Have you ever gazed at the night sky and marveled at its vastness? As it turns out, the universe is far more expansive than our eyes can perceive. In this video, we'll embark on a cosmic journey with renowned physicist Brian Cox as our guide, exploring the mind-boggling scale of the universe, its origins, and the intriguing question of what might have existed before the Big Bang. Our journey begins with the Hubble Deep Field image, a remarkable photograph that revolutionized our understanding of the cosmos. Captured by the Hubble Space Telescope in 1995, this image reveals a seemingly empty patch of sky filled with over 3,000 galaxies, each containing billions of stars. It's a humbling reminder of the sheer immensity of the universe. To put things in perspective, our own Milky Way galaxy is home to an estimated 100 to 400 billion stars, and it's just one of the trillion galaxies in the observable universe. The distances between these celestial objects are equally staggering. Light, the fastest known entity in the universe, travels at a speed of 186,000 miles per second. Yet, it takes light thousands of years to traverse the expanse between galaxies. The Andromeda Galaxy, our closest galactic neighbor, is a mere 2.5 million light-years away. However, the most distant galaxies observed by telescopes like Hubble are billions of light-years away, meaning the light we see from them began its journey long before Earth even existed. As we contemplate these cosmic scales, it's worth noting that our observable universe, vast as it may seem, is only a fraction of the entire universe. The observable universe is limited by the distance light has traveled since the Big Bang, estimated to be around 93 billion light-years in diameter. Beyond that, there could be countless more galaxies and wonders waiting to be discovered. Brian Cox, in his captivating documentaries and lectures, often emphasizes the importance of understanding these cosmic scales. By grasping the enormity of the universe, we can better appreciate our place within it and the incredible scientific advancements that have allowed us to unravel its mysteries. As we delve deeper into the cosmos, one of the most fascinating discoveries is that our universe is not static, but rather expanding at an astonishing rate. This revelation, first made by Edwin Hubble in the early 20th century, has transformed our understanding of the universe and raised intriguing questions about its nature and future. At the heart of this discovery lies the concept of redshift, a phenomenon closely tied to the Doppler effect. You might have noticed how an ambulance siren changes pitch as it passes by, with the sound waves compressed as it approaches and stretched as it moves away. Similarly, light waves from distant galaxies undergo a stretching effect, shifting towards the red end of the spectrum as they travel through the expanding universe. Hubble's groundbreaking observation of redshift in distant galaxies led him to conclude that the universe is expanding uniformly in all directions. The farther a galaxy is from Earth, the faster it appears to be moving away from us, as indicated by its redshift. This relationship between distance and redshift, known as Hubble's law, has become a cornerstone of modern cosmology. But what's causing this expansion? Scientists have proposed the existence of dark matter and dark energy, two mysterious components that make up the bulk of the universe. Dark matter, invisible to telescopes, is thought to provide the gravitational scaffolding that holds galaxies together. Dark energy, on the other hand, is believed to be a repulsive force that counteracts gravity and drives the universe's accelerating expansion. The discovery of dark energy came as a surprise to astronomers in the late 1990s. By observing distant supernovae, they found that the universe's expansion is not slowing down due to gravity, as previously thought, but rather speeding up. This acceleration implies the presence of an unknown energy that permeates all of space, pushing galaxies apart at an ever-increasing rate. The nature of dark matter and dark energy remains one of the greatest puzzles in modern physics. Scientists are employing cutting-edge telescopes and sophisticated computer simulations to unravel their properties and effects on the cosmos. Some theories suggest that dark energy could be a manifestation of Einstein's cosmological constant, a term he introduced into his equations to represent a constant energy density throughout space. As Brian Cox eloquently explains, the expanding universe and the presence of dark matter and dark energy have profound implications for the future of the cosmos. Will the universe continue to expand indefinitely, with galaxies eventually disappearing beyond the horizon? Or will the expansion slow down and reverse, leading to a cosmic collapse known as the Big Crunch? These questions lie at the forefront of cosmological research, and scientists are tirelessly working to uncover the answers. The James Webb Space Telescope, launched in 2021, is poised to provide unprecedented insights into the early universe and the nature of dark matter and dark energy. As we ponder the expanding universe and its mysterious components, we can't help but feel a sense of awe and wonder. The vastness of the cosmos, with its billions of galaxies rushing away from each other, is a humbling reminder of our place in the grand scheme of things. And yet, through the power of scientific inquiry and the brilliance of minds like Brian Cox, we continue to unravel the secrets of the universe, one discovery at a time. As we explore the vastness of the cosmos, a fundamental question arises. Just how big is the observable universe? To answer this, scientists have developed sophisticated techniques to measure cosmic distances and determine the age of the universe, allowing us to calculate the extent of the observable universe with remarkable precision. One of the key factors in determining the size of the observable universe is its age. According to the most recent measurements, the universe is approximately 13.8 billion years old. This age is derived from a combination of observations, including the cosmic microwave background radiation, CMB, and the abundance of light elements in the universe. The CMB is a faint glow of microwave radiation that fills the entire sky, believed to be an afterglow of the Big Bang. By studying the subtle variations in the temperature and polarization of the CMB, scientists can infer the age, composition, and geometry of the universe. The Wilkinson Microwave Anisotropy Probe, WMAP, launched in 2001, provided the most detailed measurements of the CMB to date, confirming the universe's age and revealing its large-scale structure. But how does the age of the universe relate to its size? The answer lies in the concept of cosmic distances. Light, the fastest known entity in the universe, travels at a constant speed of about 186,000 miles per second. By measuring how long light from distant objects takes to reach Earth, scientists can calculate the distance to those objects. However, measuring cosmic distances is not as straightforward as it might seem. The universe's expansion complicates matters, as it causes light from distant galaxies to stretch and redshift. To account for this, astronomers use a variety of distance measuring techniques, such as standard candles and baryon acoustic oscillations. Standard candles are objects with known intrinsic brightness, such as certain types of supernovae. By comparing their apparent brightness with their known intrinsic brightness, astronomers can determine their distance. Baryon acoustic oscillations, on the other hand, are regular fluctuations in the distribution of matter in the universe, which can be used as a cosmic ruler to measure distances. Using these techniques, along with data from the WMAP and other observatories, scientists have determined that the observable universe extends approximately 93 billion light-years in diameter. This means that light from the most distant objects we can observe has been traveling for about 13.8 billion years, almost the entire age of the universe. It's important to note that the observable universe is not the same as the entire universe. The observable universe is limited by the distance light has had time to travel since the Big Bang. Beyond that boundary, there may be much more universe that we cannot see, either because light from those regions hasn't had time to reach us, or because the universe's expansion has carried them beyond our observational reach. Brian Cox often emphasizes the importance of these measurements in understanding our place in the cosmos. By calculating the size of the observable universe, we can begin to grasp the immense scales involved and the incredible journey that light from distant galaxies has undertaken to reach our telescopes. The WMAP measurements, along with subsequent observations by the Planck spacecraft, have also provided insight into the composition of the universe. They reveal that ordinary matter, the stuff that makes up stars, planets, and us, accounts for only about 5% of the universe's total content. The rest is comprised of the mysterious dark matter and dark energy, which continue to challenge our understanding of the cosmos. As we explore the vastness of the observable universe, a tantalizing question emerges. Is the universe truly infinite, or does it have affinities? This question has captivated philosophers and scientists for centuries, and while we may not have a definitive answer yet, modern cosmology has provided us with some intriguing insights. First, it's essential to distinguish between the observable universe and the universe as a whole. The observable universe, as we've discussed, is the portion of the cosmos that we can see from Earth, limited by the distance light has traveled since the Big Bang. Current estimates place the size of the observable universe at around 93 billion light-years in diameter. But what lies beyond that boundary? One possibility is that the universe is indeed infinite, extending forever in all directions. In this scenario, the observable universe would be just a tiny patch within an endless expanse of galaxies, stars, and planets. However, proving the universe's infinitude is a daunting task, as we can only make observations within the limits of our cosmic horizon. Another possibility is that the universe is finite but unbounded, much like the surface of a sphere. In this model, known as a closed universe, if you were to travel in a straight line for long enough, you would eventually return to your starting point. While this idea may seem counterintuitive, it arises from Einstein's theory of general relativity, which describes gravity as the curvature of space-time. The shape and fate of the universe are intimately connected to its density and expansion rate. If the universe has a critical density, it will continue expanding forever, but the expansion will slow down over time. If the density is below the critical value, the universe will expand forever and eventually cool down to absolute zero, a scenario known as the Big Freeze. Conversely, if the density is above the critical value, the universe's expansion will eventually halt and reverse, leading to a cosmic collapse called the Big Crunch. Current observations, including measurements of the cosmic microwave background and the distribution of galaxies, suggest that the universe is very close to the critical density. This means that the universe's expansion will continue indefinitely, but it may not necessarily be infinite in size. The concept of an infinite universe also raises some mind-bending paradoxes. If the universe is truly infinite and has an infinite number of galaxies, then there should be an infinite number of copies of Earth, with variations of you living out every possible scenario. This idea, known as the infinite universe theory, is a consequence of the assumption that matter can only arrange itself in a finite number of ways within a finite volume of space. However, the infinite universe theory relies on several assumptions, such as the uniformity of the universe's laws and the absence of cosmic boundaries. Some scientists argue that the universe may have a more complex topology, or that quantum mechanics may impose limits on the configurations of matter at very large scales. Brian Cox, in his discussions of the universe's size, often emphasizes the importance of observational evidence and the limits of our current knowledge. While we may never know for certain whether the universe is infinite, we can continue to refine our theories and observations to paint a more accurate picture of the cosmos. The question of the universe's infinitude is not just a scientific curiosity, but also a profound philosophical and existential query. It challenges our understanding of reality, our place within the cosmos, and the nature of existence itself. As we continue to explore the universe and push the boundaries of our knowledge, we may uncover new insights that reshape our perception of the cosmos and our role within it. So, the next time you gaze up at the night sky, ponder the possibility of an infinite universe, filled with endless wonders and mysteries waiting to be discovered. Whether finite or infinite, the cosmos remains a source of endless fascination and inspiration for curious minds like Brian Cox and all those who dare to explore its depths. As we delve deeper into the mysteries of the cosmos, one tantalizing possibility that has captured the imagination of scientists and the public alike is the idea of parallel universes. The concept of multiple universes, or a multiverse, has gained traction in recent years, fueled by advances in theoretical physics and cosmology. The idea of parallel universes is rooted in the many-worlds interpretation of quantum mechanics, proposed by physicist Hugh Everett in 1957. According to this interpretation, every time a quantum event with multiple possible outcomes occurs, the universe splits into multiple branches, each representing a different outcome. In this view, there exists an infinite number of parallel universes, each with its own unique history and physical laws. Another approach to the multiverse idea comes from the theory of eternal inflation, which suggests that our universe is just one of countless bubble universes that emerge from a vast, inflating cosmic landscape. In this scenario, each bubble universe may have its own distinct properties, such as different values for the fundamental constants of nature, or even different forms of matter and energy. The search for evidence of parallel universes is a daunting task, as these hypothetical realms are, by definition, disconnected from our own. However, scientists have proposed several ways in which the existence of a multiverse could be indirectly inferred. One possible avenue is through the study of the cosmic microwave background, CMB, the ancient light left over from the Big Bang. Some theories suggest that collisions between neighboring bubble universes could leave imprints on the CMB, such as circular patterns or anomalies in the distribution of temperature fluctuations. While no definitive evidence of such collisions has been found, the search continues with increasingly precise measurements of the CMB. Another approach is to look for signs of extra dimensions, which are predicted by string theory, a framework that attempts to unify quantum mechanics and general relativity. According to string theory, the fundamental building blocks of the universe are tiny, vibrating strings of energy that exist in a higher dimensional space. If extra dimensions exist, they could potentially provide a pathway to other universes or even influence the behavior of particles in our own universe. The idea of parallel universes also raises fascinating philosophical questions about the nature of reality and the role of chance in shaping our existence. If there are indeed infinite universes, does that mean that every possible version of ourselves exists somewhere in the multiverse? Are there universes where the laws of physics are radically different, or where life never emerged at all? These questions are the subject of ongoing debate and speculation among scientists and philosophers. Some argue that the multiverse idea is untestable and therefore falls outside the realm of science, while others maintain that it is a natural consequence of our current understanding of physics and cosmology. Brian Cox, in his discussions of parallel universes, often emphasizes the importance of distinguishing between scientific speculation and empirical evidence. While the idea of a multiverse is certainly intriguing, he cautions against accepting it as fact without sufficient observational support. At the same time, Cox recognizes the value of theoretical exploration and the role of imagination in pushing the boundaries of our understanding. By considering the possibility of parallel universes, we are forced to confront the limits of our knowledge and the vastness of the cosmos beyond our own experience. As we continue to probe the mysteries of the universe, the search for parallel universes remains an active area of research and speculation. From the study of the cosmic microwave background to the exploration of extra dimensions, scientists are using every tool at their disposal to unravel the secrets of the cosmos. Whether or not parallel universes exist, the very idea of them challenges us to think beyond the confines of our everyday reality and to embrace the possibilities of a universe far stranger and more complex than we ever imagined. As Brian Cox reminds us, the story of the cosmos is a story of discovery, wonder, and the enduring human quest to understand our place in the grand tapestry of existence. As we ponder the vast expanse of the cosmos and its billions of galaxies, a profound question arises. What ultimate fate awaits our universe? Will it continue to expand forever, or will it eventually collapse back in on itself? Scientists have proposed several scenarios for the universe's final destiny, each with its own unique implications for the future of space and time. One possible fate is known as the Big Freeze, or heat death. In this scenario, the universe continues to expand indefinitely, becoming increasingly cold and empty as stars exhaust their fuel and galaxies drift apart. As the expansion accelerates, driven by the mysterious force of dark energy, the universe approaches a state of maximum entropy where no useful energy remains to sustain life or any form of structure. In the far distant future, the cosmos would be a vast dark void, populated only by the fading remnants of once brilliant stars and galaxies. Another potential outcome is the Big Rip, a scenario in which the accelerating expansion of the universe becomes so extreme that it eventually tears apart all matter, from galaxies and stars to atoms and subatomic particles. This would occur if the dark energy that drives the expansion increases in strength over time, leading to a runaway effect that ultimately rips the fabric of space-time itself. In this case, the universe would end in a kind of cosmic cataclysm, with space and time themselves disintegrating into a state of pure chaos. On the other hand, if the density of matter in the universe is high enough, gravity could eventually overcome the force of expansion, causing the universe to collapse back in on itself in a big crunch. In this scenario, galaxies would begin to draw closer together, stars would collide and merge, and the universe would become increasingly hot and dense as it shrinks towards a final singularity. Some theories suggest that a big crunch could be followed by a new Big Bang, giving rise to a cyclic model of the universe in which expansion and contraction alternate in an endless cosmic dance. A more exotic possibility is the Big Slurp, a scenario in which the universe is fundamentally unstable and prone to a sudden phase transition. This could occur if the Higgs field, which gives particles their mass, is not in its lowest energy state, but rather in a false vacuum state. If a bubble of lower energy true vacuum were to appear somewhere in the universe, it would expand at the speed of light, destroying everything in its path and altering the very laws of physics. In this case, the universe as we know it would be swallowed up by a rapidly expanding bubble of new cosmic order. The ultimate fate of the universe depends on several key factors, including the density of matter and energy, the nature of dark energy, and the fundamental laws of physics that govern the cosmos. Current observations suggest that the universe is flat and will continue to expand forever, favoring a big freeze or heat death scenario. However, much remains uncertain about the properties of dark energy and the behavior of the universe on the largest scales, leaving room for other possibilities. The implications of the universe's final fate are profound, not only for the far distant future, but also for our understanding of the nature of existence itself. If the universe is destined to end in a big freeze or heat death, it raises questions about the ultimate meaning and purpose of life and the cosmos. If the universe is cyclic, eternally expanding and contracting, it suggests a kind of cosmic renewal and the possibility of infinite cycles of creation and destruction. As Brian Cox eloquently explains, contemplating the possible fates of the universe is not just an academic exercise, but a deeply human endeavor that touches on our most fundamental questions about the nature of reality and our place within it. By studying the cosmos and unraveling its mysteries, we not only expand the frontiers of scientific knowledge, but also gain a deeper appreciation for the beauty, complexity, and fragility of the universe we call home.